Laws of probability. In this lesson, we're going to learn a couple new laws and then apply it to everything we just did. So we're going to apply it to Venn diagrams, we're going to apply it to tree diagrams, all that stuff. And the first law is the disaddition law, which states the probability of A or B equals probability of A plus probability of B minus the intersection probability of A and B. This law is probably the most important one because you can use it all the time. All the time. It's in your formula sheet. It's actually right here. Right here's a little section from your formula sheet. Combined events, right? That's what they call it in the formula sheet. We're gonna learn about mutually exclusive events, conditional probability, which is probably your least favorite, and independent events. This is the only one that always works. Always. It's your best friend. Anytime you have a question, you're trying to figure out what A is or B is, most of the time, you use this formula. This one always works. It's always valid. These other ones we're going to talk about it, they don't. You can only use this if they happen to say mutually exclusive, and then you can use this formula. If they say independent events, then you can use this formula. If they ask you about given that or conditional probability, which again we'll talk about more in detail later, then you can use this formula. This one they're not going to tell you, like, hey, you need to find the intersection of these two. A lot of times this is how you can do it, especially when you want to find the union, or if you just want to find a certain thing you're not sure. This is the one you're going to get to. This one's so important. This is your default. Always go here, right? Always come back here. So important. So important. Okay, I'll let you go with that. But that's the idea. Just want to always keep that in your head because that one, again, always works. Use it for so many things. So, let's do an example. So right here, this is an easy example, but they say, hey, probability of A equals 0.6, the union equals 0.7, intersection equals 0.3, find the probability of B. So we just put down the formulas. Like, I know how to do this. I got this. I got a formula to use. It's my best friend. Always works. Right? So you write down the formula. I'm going to reduce a lot in this lesson. You plug in your values. 0.7. Union is 0.7. Probability of A. Notice this is probability, not number. So it's a decimal. It's like a number. Probability of A is 0.6. Probability B, I don't know. Let's say probability of B minus the intersection. So the intersection tells me it's 0.3. Then you just do some math. You go, okay, 0.7 equals 0.6 minus 0.3, so 0.3 plus probability of B. Subtract that from both sides. And you get 0.4 equals the probability of B. Like that. Again, we're going to use this formula a lot. So much. And we're going to use it later. We'll go back to it in a bit. Okay, let's look at the next law. Mutually exclusive or disjoint events. We kind of talked about this before. Mutually exclusive means that they have nothing in common. So literally when they say that, you just want to think this, right? The intersection is 0. That's what I think of when I say mutually exclusive. Like, okay, that means they have nothing in common. Nothing in common. So the internet is 0. Right? They give you an actual formula for it. We will use it when they want. A lot of times we use this when they want you to prove, or they'll say show these two are mutually exclusive, or they might ask you, are these two mutually exclusive? So you use this one. But really, when I'm working with this, I just use our best friend here, and I know, oh, this is 0 because it's mutually exclusive. Then you can solve it like normal, like okay, plug that in, plug that in, plug that in. So it works either way. Again, you only use this if they specifically ask you or tell you, hey, it's mutually exclusive. When you hear those like special phrase, you do this. And that's the idea. So let's do an example. Or look at an example, actually. So look at this one. A chocolate is randomly selected from a box which contains 6 chocolates with hard centers and 12 chocolates with soft centers. So keep that in mind. Some of them are hard to eat. Some of them are pretty easy to eat. Let H be the event that randomly selects a chocolate from a box that has a hard center, S being the event that you select the soft center, right? So probability of H is like 6 out of 18. Probability of S is like 12 out of 18. Are events H and S mutually exclusive? So generally when they ask this, you want to use the formula. Now in this case, it's more of a theoretical question. So no, this is where I would use the formula that we just talked about. So probability of A plus probability of B equals the intersection. Start the union. right? But in this case, it's more just a theoretical question. They just want to make sure you know it's mutually exclusive. Hey, you can't have a card that has both, you can't have a candy that has both hard and soft center. I'm a little dubious. I think that there could be. I believe in chocolate technology, but I guess they don't. Then right, they want you probability of H. That's easy. 6/18. Probability of S. 12/18. And then look at the intersection. Right. Well, they have nothing in common, so 0. And then if you want to find the union, again, we could just use our formula, either this one or my. Use my best friend. Only friend. Kidding, kind of. Right here. Probability. That's sorry about the ugly H. Plus probability of S minus the intersection. Right. This is 0. S we talked about is 12/18. And H is 6/18. If you add them up, you get 18/18. Or 1. So that's how you do that. So conditional probability. This is one we're going to talk about a lot. It's so useful in lots of many different things. And I would love to ask it. The general idea is they'll tell you something like, hey, so like right here you have A and B. They'll say, hey, B happened. Like we drew a red card. What's the odds it's an ace? Stuff like that. So it's what's the odds of something happening given something else already happened, given that. So the way they write it's like this. Basically that line is given B, given that B happened. That's what's that. I don't know where I was going with that extra H at the end. Given that B, given that B happened. Right, that's the way you want to read that line. If I see like X line Y, I'm like, okay, X, given that Y happened. So Y happened, what's the odds X is going to happen? Now there's a formula for this. It's in your formula sheet. It's right here. And it kind of depends on the problem. Sometimes, like we did this already with the boxes, with the box data. I forgot what it's called. Forgive me. But like where you just go, okay, it's given B happens. You just look at the column with B in it, and that's your total. Sometimes it's easier to just think about it logically. We'll do an example over here. But sometimes I just use the formula because it's a kind of simple formula actually. You're looking for this, so that's generally your X. That's what you're looking for. The probability of A is over here. Right, whatever that happens to be. And then this is the intersection, which you usually could find. You use our good formula up there to find it also. And all you have to do is plug stuff in. So we're going to do lots of examples of this. I'll show you some where you can kind of think about it logically. Okay, this happened. What's the odds of this happening? And I'll give you some other ones where you just use the formula. Let's look at our first example here. So find the probability B given A. So again, let's listen to this logically. They're saying that A happened, right? Find the probability that B given A happened. So this happened. So that means your total, remember our favorite rule, 1 over total, is going to be all of A. Remember, all of A is all that circle, not just the 0.4, the whole part of it. So the total is 0.7. Because we know A happened. Now the question is, what's the probability of B happening? Well, here's B. Only part of B that's part of A is this right here. So 0.3 or 3 over 7. And that's the idea. Like again, given that's not that bad with Venn diagrams. It's a little worse with tree diagrams, and we'll do that. But with Venn diagrams, it's not that bad. But let's also do it with the formula, so you can see it. So the formula is this right here. I'll write it out in a second. Like that. And okay, so let's fill it out again. Right here is this is what you're looking for. B given A happened. The formula says it's like you notice this part's always the second one. The second one, so given that's always the one right here. Probability of A, well, probability of A is all this, so 0.7. Intersection of A and B, well, that's 0.3. Divide by it, 0.3 over 0.7, also known as 3/7. Right? That's the idea. Now let's do the same thing with this other example, right? Same concept. Let me erase real quick. There we go. Behind the scenes of me making videos. So find probability A given B. Sorry, probability A given B. So again, we can think about it the same way logically. We go, okay, we're given B. So we have all this. So my total, 1 over total, is going to have to be 0.5 because I know I have B. So I know I'm in B. Then what's probability of A? Well, only part of A that's in B is this right here. So 3 out of 5. If you're gonna use the formula, here's the key thing. This is part of the reason why I'm doing this. The key thing is you have to adjust this formula. You can't just use the formula that they have there. Right? It's not the same question. So in this case, this is probability of A given B. So now that changes this thing. This has to be the B now. See how it's the A was there, now it's the B. So you switch this. This side intersection doesn't matter. It doesn't matter what's on what. It doesn't matter what letters on which side, but people freak out, so I'll switch it too. But it doesn't matter. Like that. Right now, if you plug it in, again, this is the thing you're looking for. So I'll put an X down here for that. The probability of B, well, all of B, so 0.5 equals intersection 0.3. Divide by that, you're gonna get 3 over 5. So it works either way. So that's how you do given that with the Venn diagram. Not the hardest thing in the world, but it will be super relevant. So let's do another basic example. In a class of 25 students, 14 like pizza, 16 like iced coffee. One student likes neither, and 6 students like both. How can you not like pizza? Okay, whatever. One student is randomly selected from the class. What is the probability that the student likes pizza? Unless you're that freak. So let's make a Venn diagram. Now, how do you know it's a Venn diagram, not like a tree diagram? The kind of key's right here. They tell you there's a total of 25 students. That's not going to, for the most part, that's not going to be a tree diagram. They're like, oh, there's 25 students, 14 like this, 16 like this. You could tell right away, like, this is a Venn diagram. There's some that like this thing, there's some like this thing, there's some that like both. Another giveaway, hey, there's people like both of them. Maybe that's the intersection. Alright, so let's draw a little Venn diagram here. Here's pizza, yay. Here's iced tea, right? Now, iced coffee, sorry. Now it says there's 25 students in total, so that's our universe. Our universe is 25. And 14 like pizza. Now, again, 14 like pizza, that's very important. It's not this right here. That's people that only like pizza. 14 like pizza, that's the whole circle. So that's right here. Same thing with iced coffee. 16 like iced coffee. More people like iced coffee than pizza? Okay, sorry. 16 like iced coffee. Shenanigans. So right there. One student likes neither. Freak. And then 6 students like both. So that's kind of that's the key to this whole problem right here, right? 6 students like both. That's right here. Once you get that, everything else is easy. Oh, there's 14 like pizza, 6 like both. So there's only 8 that like only pizza. My people. There's 16 people like iced coffee, 6 that like both. So 10. So now you have your Venn diagram. You can solve anything you want. Once you have this set up, the world's yours. Right? So like pizza, well, pizza is all this, 14. Probability, so over total, 1 over total, 25. Over here, likes pizza, given that he or she likes iced coffee. So again, that's a given that. This is basically the same probability. Pizza, given that iced coffee. Right? So again, 2 ways to do it. One way is you know you like iced coffee. So this is your world now. So 16. What's the probability of pizza? Well, in this world here, only 6 people like pizza. 6 out of 16. Again, IB, you don't have to reduce it. If you're using the formula, right, just use the formula. So it'll be probability. I'll just write the formula down so you can see it. And we'll adjust it. Yeah, I have that memorized. Look at that. So, probability B intersects iced coffee. So, right, this is probability pizza. This is iced coffee, which makes this iced coffee. And then pizza and iced coffee. Again, it doesn't really matter here. Right? So, this is what you're looking for. Probability of iced coffee is 16. There's 16 iced coffee. Well, probability of iced coffee should be 16 over 25, technically. And then probability of pizza and iced coffee at the intersection. So that's 6 out of 25, right? Because it says probability. Multiply by the reciprocal. So multiply by 25 over 16. This is always going to cancel out, so I almost forgot to write it. And you get 6 over 16, the same answer. So that's the idea with that. Next example. Look at this one. If probability of x equals 0.6, probability of y equals 0.5, and the union equals 0.9, what is the intersection? And how are we going to do this one? With our best friend, that formula. Right, the one that always works, only one that always works. A union B equals probability of A plus probability of B minus the intersection. Right? Again, only formula that always works. Always works. I mean, it's always applicable. You might not need it, but it always works. So the union, I don't have to rewrite it. So 0.9 probability of A. Let's make this x and y, I guess. So 0.6, 0.5, and this is what I'm looking for. Do a little math. Subtract. Negative 0.2. Oh no, you can't have a negative probability. It's alright. It's gonna cancel out. Math is awesome. There you go. Right. So just don't forget that formula always works. And it's gonna come up again, but it always works. Let's move on. In a class of 40 students, 34 like banana, 22 like pineapple, 2 dislike fruits. So, 2 dislike fruits? Okay, whatever. But look at the type of problem. Venn diagram, right? 40 students, 30 like this, 22 like this is a Venn diagram again. So, we're going to draw another Venn diagram. You can tell these are super important. Right? This is 34. This is bananas. This is pineapple, right? And now again, 22 like pineapple, that is not this side, that it's the whole circle is 22. There's people that only like pineapple, that hate bananas. 2 dislike fruits. 2 people are not humans. A student is random. So you like to find probably that the student likes both fruits, blah, blah, blah. Okay, there's a reason I want to do this one. And I'm like, oh, we just did one. There's a reason I'm doing this one. I have a plan. Now notice, you have 34. You have 22. You don't have the middle this time. Right? And at the very first question is how many like both fruits? So how you can find the middle? There's only one way. And that's to call our best friend up. Use this formula. That's the union actually. Probability of A plus probability of B minus the intersection. Alright, so let me refine that to be what we're doing. So probability of banana or pineapple equals the probability of banana plus probability of pineapple minus the intersection of banana and pineapple. So like that. Now there's a couple things. You're like, okay. Now probability, again, it should be fractions. It's just technically, I always just kind of put the numbers. Okay, so let's do this right now actually. If we just look at the numbers, you don't have to do fractions, just make them all n. Right? That just says the number in here. The formula still works. Number in there. So if I put a little n there, I don't have to worry about fractions. Just use numbers. So 34, 22. This is what I'm looking for. Now you go, wait, I don't know what the union is. If I don't have that, how do I know the union? Well, think about this logically, right? This whole thing is 40. There's only 2 things here. There's the circles and then there's the outside. Here's a rule. I think we said it before. The universe equals the union plus the neither. It's the only thing that's on the board here. It's the circles, which is the union, and the neither. It's only thing, all that together equals the universe. So in this case, this is 40. I don't know what this is. This is 2, right? There's 2 on the outside. Subtract it. The union equals 38. This again, just think about logic. This whole thing is 40. There's 2 on the outside. That must be a total of 38 here in these circles. Has to be. So this is 38. Right? The whole thing is 40. Outside is 2. union, that's 38. That's how you can always find it. If you know what this is, you know what that is, you can figure out what this is. Like this formula always, it's another formula that kind of always works for Venn diagrams. So if you do this, you get 38 equals, let's see, 56 minus x, subtract 56, and I get 18 equals x. Again, I took away the negatives already. So this middle right here is 18. Again, that's the key to this whole problem. Once you get that to 18, this is 22. So 22 people like pineapple, 18 like both, so only 4 like pineapple. I prefer that 4 right there. 34, 18, so subtract, you get 16. 6 people like only bananas. And then you can answer the rest of this question. Find the probability that you like both fruits. Well, 18, don't forget it's probability over 40. Like at least one fruit. Okay, so that's right, it's like vocab, at least one. That's the union, right? You like bananas, you might like pineapple, like one of those, right? Or also, it's the opposite of liking no fruits, right? Opposite of that is liking at least one. So this is a union of pineapple and banana, which is, we figured out right here is 38. 38 out of 40. Likes bananas, given that she likes pineapple. I would use the formula to show you, but I'm running out of space. So let's see. Likes banana, given that she likes pineapple. So you know you like pineapple. So you're in this little circle here. You like this for sure. What's the odds you like bananas? Well, 18. 18 out of... Given that you like pineapples, right? Your world is now pineapples. 18 out of 22. Right? Your world is pineapples now. You know you like pineapples, so your odds are out of 22. And then the last one, dislikes pineapples, given that he or she likes bananas. So you know you like bananas. So we get the blue going. Right? So you know you like bananas. It's out of here. But it says you don't like pineapples. So here's pineapples, right? So you don't like it. So it's gonna be 16 out of 34. Let's look at that with the formula. Like that. Now look what it says, given that she likes bananas. So this part's bananas. That's kind of funny. Right? This likes pineapple. So this is pineapple prime. So a lot of this is still the same. This is your x. Bananas, 34 out of 40 or whatever. Now, here's the tough part, right? It's you don't like bananas, but you do like pineapples. Sorry, I said it wrong. You don't like pineapples, but you do like bananas. So you're looking at, okay, I like bananas, but I don't like pineapples. So you have to go, it's this part. Right? That's always B but A but not B type of thing, right? It's always bananas, but not pineapples. So no, thank you to the pineapples. So that's right there. So 16 out of 40. If you do some math, you get 16 out of 34. The hardest part with Venn diagrams is this part right here. Understanding what that stuff means. If I give you like this, but not this, this, and this, kind of drawing the picture in your head and figuring out, okay, what number do they want? Because figuring this out, not that bad. But then when they ask you stuff like, I want A and not, I want not A, not B, or A and not B, then you have to like start trying to picture and drawing those Venn diagrams. That's that example. Okay, let's do a tree diagram one. My favorites. Top shelf in a cupboard contains 3 cans of pumpkin soup and 2 cans of chicken soup. The bottom shelf contains 4 cans of pumpkin soup and 1 can of chicken soup. Lucas is twice as likely to take from the bottom shelf as he is to take from the top shelf. Suppose Lucas takes 1 can without looking at the label, determine probably that blank. So this is, I hope you can see it's a little different than the Venn diagram. They didn't tell you a total. They didn't say you have so many of these, so many of those. You kind of did. There's no and like both. There's no neither, right? This is more of a tree diagram. You have options. You could go top or bottom shelf. So we're going to draw a little tree diagram here. Here's our little shop clerk trying to decide what to pick, right? So top shelf, bottom shelf. It says that he's twice as likely to take the can from bottom shelf as the top shelf. So this is, so twice as likely. So it's 2 out of 3. This is going to be 1 out of 3. Twice as likely, so times 2, a total of 3. right? So this is 1 twice is 2, total is going to be 3 then. Let's look what we have at each shelf. So top shelf, we have pumpkin and chicken, right? Pumpkin is 3 and there's 2 chickens, so 3 out of 5, which makes this 2 out of 5. Bottom shelf, it is 4 cans of pumpkin soup. Man, they love pumpkin soup. 4 out of 5. And then there's 1 can of chicken soup, so 1 out of 5. So 4. There you go. All right, so there's our little tree diagram, and then it says it's gonna be is he's gonna pick a random chicken, right? So I'm not sure how you randomly pick top or bottom shelf, but whatever, right? You just want chicken. You're like trying to get to these things. Remember the way we did this? You go top plus chicken, so top chicken 1/3 times 2/5 plus, because there's another way you get there, bottom plus chicken. So bottom and chicken, so 2/3 times 1/5. Man, I love tree diagrams. So you get 2 out of 15 plus 2 out of 15, or 4 out of 15, as long as you know how to add your fractions. So that's the odds of getting a chicken randomly. Now let's talk about the given that. What's taken from the top shelf given that it's chicken? So you know it's chicken, right? This is, I always like to write it. Probability top given chicken. Right? That's the thing. So you know you have chicken. What's the odds of get from top shelf? See, it's not as easy. You're not like going, okay, well, I have chicken. Like with this, I just use the formula. Probability of A intersection B. Again, you have the formula sheet. You don't have to worry about memorizing like me, math stud. Okay, that's getting it out. So probability of B given A. Right, that's the formula. You have your formula sheet. You don't have to worry about memorizing it. And then I like to adjust it. So here's C, here's T, here is C, and then again, these don't really matter, T and C. So it's probability of top and chicken equals probability of chicken, probability of top given that you chose chicken. Now, here's a classic IB trick, right? So classic IB, right? What I mean by that? Probability of chicken? Well, how do you do it? It's top chicken, bottom chicken. Wait, we just did that. IB loves to use the question from earlier to help you with the question below it. So this is 4 out of 15. You already did that work, right? This is the thing I'm looking for. That's my X. Then this side, top and chicken. The way you do that, there's only one way to get top and chicken. It's going to top and then getting chicken. So 1/3 times 2/5. So you're going to get 2 out of 15 equals 4 out of 15 times X. Multiply by the reciprocal. Times 15 over 4. Times 15 over 4. And you get 2/4 or 1/2 equals X. So 2/4. And that's the way you do given that with the tree diagram. I like to use the formula a lot with this. Use the formula. Don't forget, you're generally going to use the answer from before. They love to do that. Also makes your work a little less. So that's how you do that. Okay, two more and we're done. So look at this one. In a group of 50 students, 40 study math, 32 study physics. Each student studies at least one of these subjects. I was about to say what type of problem this is, but then I read the next line. It says use a Venn diagram. So you got off easy. But yes, it's a Venn diagram. You can just notice. They give you a total. They tell you somebody do this, somebody do that. Blah, 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 blah. So let's draw a Venn diagram with the stuff we do know. We don't know everything yet. So this is math. Woo! This is physics. Boo. Universe is 50. Now again, 40 study math, that's this right here. I cannot stress that enough if you've noticed. It's the whole thing, not this. Don't be lazy. Whole thing. Physics is 32. Same idea. Right, the whole thing. Each student studies at least one of these subjects. So that's important. I almost skip that. That means that there's nothing on the outside. Right? Nobody studies not math or physics. This is a good school. So use a Venn diagram to figure out how many students study both subjects. So again, both subjects we don't have. Only one way to find it, and that's to use our best friend. Right? Use this guy. The only formula that always works. Math union physics equals probability of math, woohoo, plus probability of physics minus probability of math and physics. STEM, there you go. Right, again, talk about this. The way you get that right there, it should be 50. The way you get that right there is it's always the same. The universe equals the union plus the neither. In this case, the neither, this is union, so not the universe. The neither is 0. Right? So the universe equals 50 plus the union plus 0. So the union is just going to be 50. This is just 50. Right? If you have to study, if there's nobody studying not one of these things, well, then the union is the universe. I didn't do that the best, but we'll move on. Probability of math is 40. Again, I'm actually doing the number, not the probability, right? Number would probably be like a fraction. I'm doing the number. It works the same way. So the number of math is 40, the number of physics is 32, and this is what we're looking for. So 50 equals 72 minus x, minus 72, minus 72, negative 22 equals x, negative x I should say, x equals 22. So 22 people are studying both of these classes. Right, and then again, that's kind of the key to everything. Now notice how it says how many, not probability, so I'm just going to put 22 here, and I'm done with that one. As I just mentioned, this is the key to everything. You got 22 people, 32 people only studying physics, and 22 studying math and physics. That means there's only 10 left over that only study physics. You got these 40 people studying math, and you have 22 right there, so there's only 18 people that are doing God's work. Okay, so next part. If a student from this group is running, select to find probably that he or she studies mathematics but not physics, right? So it's all about understanding what's going on. They study math but not physics. So here's math. They study math but not physics. So they don't want these physics. It's this right here. Right? It's math and not physics, right? So math but not the physics part of it. So 18. Study physics given that he or she studies math. So physics given that they study math. Right, again, two ways to do it. You can use a formula. Probability, I'll just adjust it already. Physics and math equals probability of math times probability of physics given math. This is x. Probability of math is 40. And the intersection is 22. Right? If you know the formula, which is in the formula sheet, you don't have to know it. If you know how to use it, it's easy. If you want to think about it logically, it's just as easy, right? You know math. You know they take math. So 40. How many of those study physics? 22. 22 out of 40. That's the idea. That's how you do it with the Venn diagram. That's generally the level at which they give it to you. To finish up, let's do one last tree diagram because we only did one of those. We did a lot of N. So this tree diagram here. The probability that Greta's mother takes her shopping is 2 out of 5. When Greta goes shopping with her mother, she gets an ice cream 70% of the time. When Greta does not go shopping with her mother, she gets an ice cream 30% of the time. Determine the probability that Greta's mother buys her ice cream when shopping. So right first, this is a tree diagram. You can see again, they didn't mention any totals. They're just saying, hey, you do this or you do that. You have options in your life, right? You have paths that could split. That's a tree diagram. So we're going to draw a little Greta here. A little ice cream cone. Right? And then she could either go shopping with her mom, or not with her mom. So when she goes off with her mom 2 out of 5 times, that means most of the time her mom doesn't care about her. 3 out of 5. When Greta goes shopping with her mom, she gets ice cream 70% of the time. She tries to make up for not caring about her by buying her ice cream. So this is ice cream. 0.7. This is no ice cream. 0.3. Remember, this always has to equal 1. So 0.3. She goes by herself. She buys ice cream 30% of the time. That means that she doesn't get ice cream. A little not ice cream 70% of the time. Right, so that's our tree diagram. Find probably that Greta's mom buys her ice cream when shopping. Right, so that's a straightforward question. She goes to her mom, and they get ice cream. So it's 2/5 times 0.7. Whatever that turns out to be in your calculator, make it a fraction, 7 over 10, and figure it out. It's not too bad. I just don't care right now. Now the next one's one I really care about. Greta went shopping with her mom, given that her mom buys her ice cream. So what's the odds that her mom that her mom buys her ice cream. She went shopping with her mom. Okay. So this one's basically, I was thinking about it for a second. This one's basically gonna be, right, shopping with mom. So with mom, given that she got ice cream, So let's use the formula. Get the tree diagram. It's a lot easier to use the formula. So that's gonna be, I'm just gonna adjust it for us already. Ice cream equals probability of ice cream times ice cream given mom. Mom given ice cream, actually. That's what that says. Mom given ice cream. This is what we're looking for. Probability of ice cream, classic IB. Look at that. The one we did earlier. Actually, no, it's not. I'm wrong. Ice cream right here. Right? So there's two ways to get ice cream. So it's 2/5 times 0.7 plus, you get it this way, 3/5 times 0.3. Right? All that mess, it's some number. Sorry about it. It's getting late. I don't care anymore. And right here, mom and ice cream. That's the classic IP, right? What's probably that? So this is mom and ice cream. We just did that. Mom buys her ice cream. It's right there. Whatever 4/5 times 2/5 times 0.7 was. So you get this, and then you divide by that, and you get your answer, which I don't know right now, but that's it. That's a concept at least, right? Mom buys her ice cream. This is straightforward. Mom and ice cream. Given that, especially with tree diagrams, you want to use the formula. Mine's just ugly right here. I'm sorry, but it's right. Mom, given that you got ice cream, so it's just use the formula sheet and match it. Mom and ice cream, classic IB. They give us, did that earlier. Ice cream. How do you get ice cream? There's two ways. So remember, when there's more than one way, you just multiply those, add it to this one. So I did right there, ugly. And then that's what you're looking for. And just do some math. There we go. We are done, finally.